Bruno, boa tarde. Possa compartilhar a apresentação, por favor?
Assim, já posso começar a apresentação? Tudo ok?
Não, só por um momento.
Tá, deixa eu compartilhar.
Good afternoon, everyone. My name is Eric Quesada, Director of the SPWLA UIS Communications Committee, and I will be moderating the following session titled Petrofísica in Mature Fields in Brazil, an event organized by the SPWLA UIS and SPWLA USCO student chapters of Colombia. In this day, we will be accompanied by the speaker, Bruno Menchio, who is a geologist from the Federal University of Rio de Janeiro and graduated with honors with a master's degree in geology from the Fluminense University in Brazil. Senior petrophysicist with a background in geological operations, meeting the demands of the exploration and development sectors. Complete profile with ability to move through the various applications within the formation evaluation area. Bruno has experience in carbonate, siliciclastic, and unconventional reservoirs. His active participation in the project of acidizing tight sandstones reservoirs extends out, responsible for the introduction of the resisted imaging tool in Brazil. He is currently the Regional Director of Latin America and member of the Technical Committee of the Society of Petrophysicists and well-loved analysts, and has worked in oil companies such as Halliburton, Datalog, Geological Survey for Brazil, BLP Consulting, and INIBA. Before starting, there will be a time at the end of the presentation to ask questions, where you can turn on your microphones or write them in the chat. Then we give you a warm welcome, Director Bruno. Now you have the floor.
So good afternoon and good night for everyone. It is a pleasure for me to help you and contribute in this web meeting organized by SPAA UIS Student Chapter. So thanks, Eric, for the presentation. And this is the title of my presentation, Matter Field Petrophysics. And as Eric said before, I'm SPAA Latin America Regional Director, and actually I'm acting as an independent consultant. So we have here one agenda of my presentation. I will start with an introduction. I will show you the necessary data set, some applications, and conclusions. Introduction. So the first thing that I would like to show you is this question: why matter fields? So 70% amount of worldwide oil and gas production came from matter fields. So even in nowadays, they are the biggest reservoir that's still producing nowadays. And why Brazil? So Brazil is selling matter fields under its ongoing investment program. It includes assets on offshore and onshore. And there are many small size and mid-size companies that are investing in these assets. So independent oil companies are planning sizable investments to revitalize operations in matter fields. So what I will show you in this presentation can be applied for any conventional matter field in the world. But my motivation was Brazil, because I live in Brazil, and I'm seeing actually what is happening, the growing of new companies and selling new old matter assets from Petrobras. So thinking in petrophysics of matter fields, we have two topics that have relevant importance. The first one is reservoir monitoring. We need to understand what's happening with the production in terms of fluids, in terms of pressure, in terms of temperature. So it is really important to monitor what's happening in the reservoir, because it is something that will be very important for field management. And when I'm talking about field management, I talk about some actions that the operator can do, for example, to increase the production. We can inject water in the reservoir or inject gas, for example, and we can use technologies as enhance the oil recovery or increase the oil recovery. And of course, we need a very good knowing of the petrophysics of the reservoir to implement these technologies. So these are the first two things that I would like to mention for you that are really important for petrophysics of matter fields. So thinking specifically in petrophysics, there are three topics that are really important to understand in the matter fields. The first one is the fluids. We need to know where are the fluids, what is happening with the fluids with the time of production, if we have some movement in the water oil contact, or what's happening with the water saturation. With the time, the water saturation can increase with the production. We need to understand the temperature and pressure that can change the physical state of these fluids. Another topic that is really important is the connectivity, because some reservoirs have some geological layers that contains hydrocarbons, but sometimes these layers are not connected. And for example, we can drain oil from one zone, but there is another sand that it is in another zone that was not drained, and the sand can be drained for increase the production of a field. This is one example of the importance of the geological connectivity of layers. And of course, the main thing here is to understand the production. When we are talking about mature field, this is the most important thing, is we need to understand how much one zone of the reservoir will produce, what is the best zone to produce, what interventions we can do to improve the production, the actual production of one field. So these are the three, I can say, the three most important things for petrophysics in mature fields. And of course, we can apply these concepts for any mature field in the world. So I'll talk a little bit about the data set. This is one, we can see here 3 tables. These are the most important data sets that we will need to work with mature fields in terms of petrophysics. The first one is core. We need to have a routine core analysis, special core analysis, sedimentology, stratigraphy, and facies. So we need to have a very good model of hydrocarbons in place, and for this we need to have a good calibration between core and log data. So routine core analysis are very important. We need to understand the capillary pressure, the relative permeability, petrophysical properties of our reservoir, and we can do some integrated reservoir studies. For example, we can estimate flow units utilizing permeability and porosity from routine core analysis. And sedimentology and stratigraphy are important because we can understand the lithology. We can predict the best facies based in seismic, for example. And we can understand the depositional environment and the facies, because the facies, we can use this information to populate a static model with well logs. So this is a very important information for the mature fields. We need, of course, open hole logs, conventional open hole logs, and some special open hole logs if we have this data. And as I have mentioned before, it is really important to calibrate the petrophysical property measures by well logs with core data. So this is the basis for estimate the hydrocarbon volume in place. And we need to know the original pressure of a reservoir. We can use the white line formation tester, for example, for estimate the pressure. And we can also sample the fluids in the same zones of the reservoir. We need to understand more about the fluids that it contains. So these 2 tables represent the first part of the study. And when you start the production of a field, we use some cased hole logs that will support you in many decisions. So we have posted neutron or saturation logs that can show you and let you know to understand the distribution of the fluids in the reservoir. Production logging tools that can help you understand what are the most productive zones, what kind of fluid the determined zone is producing, and among other things. CBL, VDL, that are cement bond log, variable density log, that are tools that can use it to evaluate the cementation of well and case inspection that we can use to evaluate what is happening with case in time, because if we can have some problems with corrosion, leak, hole, that I will explain in a few slides. So now I will show you some applications for matter fields related to the petrophysics. This is a workflow thinking just in this kind of fields. The first thing, in my opinion, that we should do is refining static and dynamic model. When you receive data from matter field that, for example, your company bought from another operator, we should do this type of reservoir studies. So in my opinion, it is necessary to perform rock typing and saturation height modeling, because it is important inputs for dynamic model and static model, and it is the first thing that we should do. And we can work with these production logs after you have this task done, and there are no priority in which one will you run before. It depends of what is occurring in your field, in your reservoir. But we are talking about case hole logs, reservoir monitoring with pulse neutron, producibility that we can use production logging tools, cement evaluation, and casing inspection. So continuing this workflow, the first application is to perform rock typing and saturation height modeling. So the first thing that we should do is the volumetric interpretation. We should have a very good value calibrated with core of porosity and water saturation, because they are the inputs for hydrocarbon, volume of hydrocarbon in place. And we need to integrate with the core depth to have the best match. And this is one of the inputs for the static model. Another input is the phases. The phases come from the geologist, and the geologist can provide us information about lithology, the positional environment, and we can use that to populate this information in well logs. So we can use some techniques of machine learning to populate for example, a static model with information from logs. The second step is to do something that we can call as hydraulic flow units or rock types. These are very important for production because it is a kind of petrophysical rock typing, and we can understand the behavior of some zones related to the production. So with this approach, we use the permeability and porosity. There is one way mathematical equation that can be used to estimate these hydraulic flow units. After that, after you have a reservoir divided into many types of hydraulic flow units, you can develop a saturation height modeling. Saturation height modeling correlates permeability and porosity with the height of the oil or gas or contact. You can apply one equation, and you can have better estimates of water saturation. This is very important information for dynamic model, because the saturation height functions are a primary input in modeling the fluid distribution in the reservoir simulations. And again, we need to do this hydraulic flow units prediction using some techniques from machine learning. In this case, self-organizing maps or cluster analysis. There are another types, for example, neural networks. But in this example, there are these two types that can be used. So, and how can I perform these studies for hydraulic flow units? I will start talking about core domain. You can see here some cross plots. This is the rock quality index against normalized porosity. This information comes from core. And what we can see here is that we can divide our reservoir in 6 hydraulic flow units that have the same behavior related to port road height, to the same properties for the same permeability, porosity estimations. So this is the first thing that we should do. This cross plot, if you get the intercept of this hydraulic flow unit with the normalized porosity of 1, we can get the value of each flow zone indicator here. But the most important thing is to divide our reservoir in many hydraulic unit phases or units. And why this is important? Because when do this type of approach, we can plot here the permeability against porosity, and we can estimate the permeability for each one of these hydraulic flow units. So it becomes easier to predict the permeability if you know the hydraulic flow units and if you have the hydraulic flow units populated in your model. We can develop an equation and regression that correlate just porosity, and you can estimate the permeability. This is the first information that is very important from this approach. The second one, we can see this cross plot. This is a Lorentz plot that in this axis we have a cumulative flow capacity is the sum of permeability versus height. And this axis we have a cumulative storage capacity that's the sum of porosity versus height. What it means when we have some, for example, horizontal lines, it means that this hydraulic flow units have a good storage capacity. And if we have some inclined zones, this represents that these hydraulic flow units contribute very much for flow. In terms of production, it is really important because, for example, these hydraulic flow units are the better for production, and another ones are good for storage. The second approach here is we need to move from core domain to core log domain. We need to extrapolate this information using well logs. So this is a window of software.
Recording in progress.
Interactive petrophysics software. And we can see here the input curves, the conventional logs density, PE, compressional wave, neutron porosity, and gamma ray. And here we have the hydraulic flow units from core. And what we will do here is to calibrate the well logs with core logs to have a good match and propagate this information in another wells that I don't have data from core. This technique called self-organizing maps works with some maps. We can see some maps from many of these petrophysical or well logs curves. And we can understand the answer of each one of the hydraulic flow units that were used as input. For example, this blue zone represents the hydraulic flow unit 1. And if we correlate with these zones in the maps, you can see that we have low values of compressional waves, high values of density, high values of neutron, and also high values of PE and gamma ray. So the software uses this information for populate well logs with hydraulic flow units. Here you can see a good example, a log in the core log domain, where we have all this information integrated. In the first track, you can see the gamma ray and the caliper curve. Here you can see the density neutron, PE, and compressional wave, resistivity curve, density matrix curve, hydraulic units, unit 6, for example, have the better permeability and porosity of all these phases. So this is the best interval for productivity and other things. And if you take a look at the HFU1, that is the blue one, we have very low values of permeability and porosity. So this hydraulic units is more for storage than for flow, and this one is the better for flow. And the main idea of this study is to propagate all of this information in all the wells that you have in one major field. So when you finished your task of rock typing, we will move for the next step, that will be the saturation height modeling. We have an example here of 3 rock types, A, B, and C, that are propagated in one well, for example, and we have some capillary pressure curves for each one of these rock types. These measures were performed in laboratory, and what we can see here is that the rock type A has the better quality for reservoir. We can see that the curve is very close to this axis. This is the behavior of a good quality reservoir, and the rock type C has the bad quality for reservoir. So we can use this information as we have this rock type propagated. For example, with the well, we can use this information, this curve, to propagate the water saturation, as we can see here in this track. For example, if in the base of this column we have rock type A, the water contact will be over here because the entry pressure is really low. So because this is a very good reservoir, and the oil water contact will be here. So if you have, for example, the rock type B, we can see that the entry pressure is much higher than for rock type A. So the water contact, for example, for these phases, if it will be here, it moves for this position because of entry pressure, and we can extrapolate the same way of thinking for the rock type C. So it is quite common for the quality of the dynamic model to be more sensitive to errors in the distribution of A, B, and C in the wells than the errors in the capillary pressure curves for A, B, and C. This is very important. We need to have a very good quality control of the distribution of the hydraulic fluid units in the wells, because this is the most sensitivity information. The capillary pressure are much more robust than this type of approach. But if you have a good quality control, it can work really well. Hence, the rock effect typing is key to the effectiveness of the saturation height model. So now we have this our saturation height model for each of these rock types, and this is the approach to propagate the rock types using the machine learning techniques. So we use one of these algorithms, self-organizing maps, cluster analysis, or fuzzy logic, for example, that are models that are used to determine phases, or the same methods can use to predict phases or flow units. These are very low machine learning methods. And we can use this information to propagate the rock types. And after we have propagated, we can enter the saturation height modeling to estimate water saturation and use it in dynamic model. We will get the permeability from hydraulic flow units, for example, in this approach, but there are another ways to get this. We can use an NMR log, for example, a core perm exploit regression, or a curve prediction. But how is the reservoir engineer going to model permeability in the simulator? So we will give to the reservoir engineer the equations of permeability based on the porosity and the hydraulic flow units, and it can be directly used in the dynamic model. Here we can see some applications of rock typing for saturation height modeling. The first cross plot, we have the saturation plug, and here the J function. J function is a function that correlates permeability and porosity regarding to the height of the contact. As we can see here, the rock types, we have 4 rock types: the blue one, the magenta, the green, and the brown. And we have here the raw capillary pressure curves. And we can see that these are the best flow units, and the green one is the worst flow units. We can see the same behavior for this cross plot. And this cross plot correlates pore throat size with water saturation, with pore. I'm sorry. And we can see that the blue rock type has the biggest pore throat radius, indicating that this is the best quality reservoir with the best permeability, capillary pressure curve, among other important petrophysical properties. And we also have here another rock types, but with less pore throat radius than this one. So the blue one is the best flow unit, or hydraulic flow unit. Finally, in this approach, you can see a composite plot with all the wells that I have in this field. We have, for example, the hydraulic flow units distributed between the wells that we can see here in this track. We have the water saturation estimated by arch equation in the blue, and the red is the water saturation estimated by saturation height modeling. You can see that the curves have a very good match in these 4 wells. And we have also the permeability curve here. That is also another important curve for production to select, for example, some zones for perforate and put it in production. So this is a final plot with this information. And we can see here that the bottom of these well logs are the contact, and I have perforate and put it in production. So this is a final plot with this information, and we can see here that the bottom of these well logs are the contact, and I have perforate and point the field, put it in production. So this is a final plot with this information, and we can see here that the bottom of these well logs are production, contact, and I have contributing most to production. Yes, we need to understand that at this point there are some tools that can help production. So this is a final plot, very useful for this task. Has the oil-water contact moved since production began? Yes, this is another very important information, because we know that with the time of production, we have some changes in the distribution of fluids, and the oil-water contact can, for example, go up or moving up, and we can start to produce water in one zone that in the beginning was producing oil, but because of this moving of fluids, this zone is now producing water. Where is the water production coming from? We need to understand that what's happening if we have some problems in the cement. We can see here the well, it is the cement, it is the casing. We have a reservoir with water, oil, and gas, and these are the perforated zones of this reservoir. So we have, for example, one problem with cement here, or here, the water can enter in the well, and it can be a problem for the production of hydrocarbon. We need to understand that. Is there fluid flow in the annulus? Yes, it's the same that I mentioned it before. Is the cement providing an annular barrier between reservoir and surface? This is a very important information. We need to know that it is related to safety of the well, because we wouldn't like to have this connection from oil or gas until the surface. We need to have a barrier. It is dangerous, and it also can, for example, put hydrocarbon in contact of aquifer and can pollute these zones. So it is very important to have an annular barrier between reservoir and surface for safety reasons. So the other two questions are related to the casing. Do we have a leak, or has the casing worn over time? It is common in a field of in a life of a mature field. We can have problems of corrosion or worn with the time. So we can use, for example, the case inspection to detect these zones. And the last question is, can we increase the production by reperforating? Maybe we can understand the distribution of water saturation. For example, use a saturation log or a pulsed neutron log, and we can reperforate in one zone that still has the original oil saturation, and we can, of course, increase the production of this well. So now I will talk about specifically about the pulsed neutron. That it is one cased hole log, very important. We can see here that this tool has many applications. We can see that we have problems with water saturation in depleted reservoirs. We can detect, for example, bypassed gas zones or oil zones. We can do petrophysical evaluation of old fields, and we can estimate the current oil saturation, and understand the water production behind the casing or flow behind the casing. These are the main information that we can get from the pulsed neutrons, and there are mainly two types of acquisition. For example, if you have salt water, we can use the capture mode, and if you have fresh water, we can use the spectroscopy mode of logging. For bypassed gas zones, we can use capture with inelastic ratio. This is a technique to detect gas. I will show you in the next slide. And for this technique can be very useful for petrophysical evaluation of old fields when we have just resistivity or potential spontaneous open hole logs available. And it can help us to have a better water saturation curve. And for field management, we can think about oil saturation in reservoirs that has a gas cap, and we can, for example, inject gas to increase the pressure of the reservoir, or inject water to increase the pressure of the reservoir. And we need to also understand the flow behind the casing. If we have this problem, pulsed neutron can be a very useful tool. So the technologies used for open hole evaluations of fluid saturations are no valid on casing tubings in place. But pulsed neutron tool is a tool that was developed to work with cased hole condition. We can see one example here of a pulsed neutron tool inside the well. We have a source of neutrons, and the tool emits these neutrons against the formation, and we have two detectors, the near detector and far detector, and we can use this information to calculate or to estimate the water saturation for a zone, for example. And this tool is very used to determine how fluid saturations are changing and contacts are changing during the production life of well. This is dynamic, depending of the time that you still started the production. You see that we have some changes in contact and saturation with the time. And we have two different logging tool modes, the Sigma mode that is used for reservoirs with highly saline water, and carbon oxygen logs, carbon oxygen mode of acquisition for low or mixed water salinity. These are very important information, and and what we can see here in this plot is that we have very low values of sigma at this zone, and we have high values of inelastic ratio and hat. And this indicates that we have gas in this zone that was bypassed, but now we can perforate the zones and increase the productivity of this well with these zones. If we take a look at this table, the sigma of gas is very low, and it is what we are seeing here. We have very low values of sigma in this part of the reservoir, indicating the gas presence. And water saturation is calculated in a similar manner of material balance equation. We need to know the matrix sigma, the hydrocarbon sigma. We can get this information from this table, for example, the clay sigma, the water sigma, and the hydrocarbon sigma, and apply in this equation to estimate the water saturation. Here we can see an example of an old well that we have in one field. We just have two curves, two types of curves. The first one here is the potential spontaneous curve. The second one is the resistivity curve. And the main problem here is that we don't have any porosity curve, and it is very important to estimate the water saturation, mainly if you use the most classical equations for water saturations as RT, Indonesia, Samandu, among the others. And in this track, we can see the original water saturation in blue that was estimated based in the old logs, and the red one is the curve of the water saturation estimated by the pulsed neutron logs. And what we can see here is that the sand A is depleted, the water saturation, the oil hydrocarbon saturation is very low. And with the first petrophysical evaluation with old logs, it shows that this zone has oil that can produce oil, but the zone is depleted. We should avoid the zone for perforating because it will produce water. This zone, we can see that the curves are closed, and we have a good estimates of oil saturation. This zone has oil, as we can see here, this sand B, and we can compare these results and also in this lower zone that open hole water saturation underestimated the potential of hydrocarbon of this zone, for example, that have much more hydrocarbon than the old logs that predicted. And this zone also has hydrocarbon. And this is the importance of using pulsed neutron logs in this kind of data from old wells. Another important thing, it is another example for current oil saturation. Sometimes it is necessary to do water injection to maintain the pressure of the reservoir. And we can see here a plot, a composite plot. You can see here some perforated zones, gamma ray curve, the water saturation, and we have here the oil saturation that were estimated from open hole logs. And here we have the oil saturation that was estimated from cased hole logs. And after the production of the production of this well, they couldn't see this water that came from water injection. And when they run the cased hole logs, it is possible to see this water moving in the oil zone. And we can have a mix of salinities here. The salinity from the water formation, the salinity from the water that was injected in the reservoir. So we have a mix of salinity. So it is very difficult to work, for example, with resistivity curve to have this result. And the pulsed neutron has this advantage because pulsed neutron is independent of resistivity, and we can have a much better estimates of water saturation. This is another application of pulsed neutron that we can call time lapse. This application shows that with the time, we have the variation of water saturation, and we can take some corrective actions in our reservoir. As we can see here in this track, we have the open hole curves, or the original curves of the reservoir. You can see that we have very good oil saturations. We are in a carbonate rock or reservoir. And 1 year after that, they run a pulsed neutron log, and we can't see many variations in the oil saturation. But in the second year, we can see that we have increased the water saturation in the bottom of the reservoir. And in the third year, we also see that we have more water saturation, the increase of water saturation in the reservoir. And it is a very important information because we can select a new zones for perforate and including the production of this field. And we can, for example, shut off another zones that are producing water right now. This is an example of a commercial software that can use the information from pulsed neutron to estimate the actual water saturation. This is a sigma SW analysis model that is used to calculate behind casing water saturation from pulsed neutron data. We can use, for example, some interactive log plots and cross plots that allow for the interactive selection of key parameters. And results are updated in real time as parameters are adjusted. It looks similar to the density neutron cross plot, or for example, the Pickett plot, where we have some zones here that we know that are water zones, and we can use these lines to calibrate this zone. This is the same 100% water saturation for this zone, and we can see that this zone that in the past had oil, because we can see the original curve, that is the blue one, and now this zone is depleted. It's this zone we will produce just water right now. But if we take a look at this upper zone still has some oil saturation, and we could do some corrective actions to produce from these zones. And if we need, we can close another perforations that are in these zones. So we also can do a time-lapse version of Sigma mode that are available in interactive petrophysics, and there is one very interesting module that's coming, that will be the IP carbon oxygen module, that will be very useful for working with these matter fields. And in my opinion, it will be very useful for matter fields in Brazil that we have many of wells with this information. So now I will move to the applications for the production logging tool. As I have showed before, this is important to have a study of hydraulic flow units. This is one example of this study in one reservoir. We have the permeability against porosity, and we have 4 rock types here. You can see that the brown one is the best reservoir quality. We have the higher permeabilities, and the green one is the worst hydraulic unit phases. And we can see here that this study we have a Lorentz plot, and we can see that hydraulic unit 1, 2, and 3 contribute more to storage, and hydraulic unit hydraulic unit 1, 2, and 3 contribute more to storage, and hydraulic unit 4 contribute more to flow. The hydraulic unit 1 contribute more to flow. And we can see here the PLT answer from a flow meter or a spinner flow. And what we can see is that the brown dots are the hydraulic unit 1. That is the transmissibility dominated, that is the best one. And we can see the inflow of the fluid when the spinner passes in front of this hydraulic units. So we can use this information to check our hydraulic flow units model, if this is okay with the PLT information, and if we can make some adjustments if it is necessary. Now I will show you some applications that are related to production. As we can see here, we have one zone with high pressure that are producing oil, and this zone and the above zone we have one zone with high with high permeability and low pressure, and if oil enters in the well, they will enter again the formation because of this low pressure zone. So we will have lower than expected oil production. The possible causes cross flow or teeth zones, and we can use the production log for diagnosis. So guys, I think in more 10 minutes I will finish this presentation. Is it okay?
Yes, Bruno, it's okay.
Okay, thank you. Another problem that can occur is that we can have some void in the cement, and the water from the reservoir can enter in the cement, and of course it will increase the production of water and gas. It is unwanted fluids that are entering in our well, and the name of this is channeling. So we can use some production log or cement bond log to identify the zones and perform some corrected actions to solve these problems. Another problem is the coning. As we can see here in this picture, we have coning of water here in the bottom, and in the top we have coning of gas. The possible cause here is the drawdown that's too high, and we have a higher than expected gas or water production, and the production log can detect this coning, also with saturation log that we can see the changes in the saturation in the zones. This is another common problem here when we have some hole or leak in the casing, and the water can enter in the well, so we have a higher than expected water production. The possible cause is the casing leak caused by corrosion or damage, and we can use the case inspection log and production log to solve this problem or detect this problem. Another problem is related to permeability. There are some intervals that have good permeability and will produce easily, and there are another intervals that can have low permeability and won't produce nothing. So this is very important to understand the permeability of your reservoir to avoid this kind of situation. And we can use, again, PFT and case inspection log for this task. Another thing that can happen is that after the perforation, after we perforated the reservoir, we can blockage the perforations with gun debris, crushed rock, or mud cake. And as we can see here, just some of the perforated zones will produce hydrocarbons, and another one is blocked by some of these materials, and we can use inspection log or production logs for that. This is one plot example. We have a reservoir with water, oil, and gas. We have some perforations here. This is the PLT logging tool that has many sensors, flow meters, spinners, temperature, pressures, capacitance, resistivity. And this is the plot of the results of this tool. We can, for example, understand the flow rate. We can see here that this zone that is related to this perforation is producing water. This zone is producing oil, and this one is producing gas. We can use some sensors to identify the type of fluid. For example, here we have the density of fluids. Water has higher density than oil, and oil has higher density than gas, when we can use it to understand what type of fluid is entering in the well. And here we can apply some mathematical equations to estimate the production of gas, of oil, and of course water is not important, but we can estimate it also for water. And this is just the same thing, but show it in the position of the perforated zones. When we are talking about horizontal wells, the things become difficult because we have some vertical zones, we have some horizontal zones, some upward horizontal zones, downward horizontal zones. And as we can see here, we have some perforation zones in this interval. And we have, we don't mix, for example, gas with water. This is the heavy phase that it is water, and this is the light phase that it is gas. And we have a flow coming from these perforations. And as we can see here, the pattern of distribution of the fluids in the well is very heterogeneous. So the common approach for production log tools won't work here. We need to use tools that are much more sophisticated, that have multi-sensors, that we can get the orientation of the sensors, and we can understand if, for example, in the top side of our horizontal well is producing gas, and in the downside we have water. So we have these tools, for example, CAT that use capacitance, RAT that use resistivity, and this is the approach for the horizontal wells. The CBL, VDL are very important also. We have here one example of a well that has very good cement. As we can see here, these are the perforated zones, and the oil is entering in the well and going to the surface in the normal way. So everything is okay, but if we have some problems related to bad cement, you can see that the water can enter in this perforation, gas can enter in this perforation, and it is bad for production. And what can be very dangerous, gas can go to the surface if we don't have a barrier here. So cement is a very important issue in major fields. These are some perspectives. For example, if a well with a good cement covering 306 degrees of a well, of this well, we can see that we have a partial bonding. This zone don't have cement, so it can create channeling that are preferential paths for water to enter in the well. And what are the main physics for that? This is a very simple way to explain that. If you have, for example, a bell ringing, when we hear it with high amplitude, with a very clear sound, this ring is this bell is ringing with liberty. And for example, if we have a bell ringing and there is something that is attenuating the ringing of this well, for example, someone that is with their hands on the bell, we can have a lower amplitude or an attenuated sound. And there are two main basic curves that are used for interpretation of cement logs. This zone, for example, has free pipe. We don't have any cement here. It has high amplitude because the casing has liberty for move in this zone, for example, and it generated a clear and high amplitude signal. And we have this zone that have a very good bonding between the casing and the formation. The cement is very good here, so we have low amplitudes. And of course, there are other intervals with partial bond and poor bond that are the intermediate between these two situations. The variable density log, you can see here that we can have four types of cementing, or we have, for example, free pipe that without we have any cement, and we can see this variable density log with high amplitudes without attenuation. If we have good bound, we can see some attenuations in these amplitudes, showing the good presence of bond. If we have some partial bonds, we can see the variations. For example, here we can see the sign of free pipe, but the zones are attenuated, and we can detect the zones that have good cementation and the zones that had poor cementation. And if you have just cement covering the casing, and it is not in contact with the formation, we wouldn't see any amplitude here. This is one example of plot, a very basic example of cement mode log and variable density log. thinking in the same way of the things that I told you before. We can see the amplitude curve here, the variable density log here, and we have a high amplitude indicated free pipe, and high amplitude you can see for variable density log, and low amplitude, and we can see the effect of attenuation here, indicated that this zone has good quality of cement. And finally, the last tool that I would like to show you is the case inspection. This tool has multi-fingers or calipers that are entered in the well and can understand what's happening inside the casing. With the time, we have some problems related to leak, hole, or worm, and these tools can help us to understand what's happening in the casing with the time, and we can take some corrections for avoid, for example, water production. These are very important tools, and it is important to have the orientation of the tool, because we need to understand in which portion of the casing we have problems. Here you can see one example of this tool. You can see over here that some zones of the casing are out of the gauge. The yellow curve shows the gauge of the casing, indicating that we have some problems, and these maps here show us the zones that has, for example, some holes or leaks in the casing. Finally, some conclusions. Major field petrophysical applications must be performed with core data, open hole, and cased hole logs. We should do some core log studies for understanding the behavior of our reservoir, and can be used also for increments, studies of reserve increments that have a financial impact on the major field. And saturation height modeling are essential for this type of study. Pulse and neutral tools can be used for bypassed and undrained zones. We can understand what's happening in terms of fluids, distribution of fluids, if the contact is moving, if the water saturation is increasing. The production logging tool helps to understand the productivity of the zones and can be correlated with the hydraulic flow units to calibrated responses based on permeability. And we also have production-related problems that can be solved with the use of this tool. And we can use CBL, VDL, and case inspections for understanding the cementation, and casing issues. And so the theme is broad and involves many topics. In addition to this presented, there are other applications, geosteering applications in horizontal wells, petrophysics of high angle, horizontal wells, enhanced oil recovery, increased oil recovery to increase the recovery factor, among others. These applications presented here are the most common in the major fields. So thank you very much. My email is bruno.menchio@hotmail.com, and any questions. I'm sorry about the time, but I am here to listen to some questions.
Don't worry, Bruno, for the time. Thank you to you for the presentation. That was an excellent and interesting performance. And we had one question in the chat. Let me read it. From Oscar Piraneke. Bruno, excellent presentation. SHN seems to be a good approach for continuous sandstones and where we had plenty information of contacts. My question is, how to manage compartmentalized fields with several contacts and low vertical continuity?
Yes, this is a very good question. Petrofísica is a very good tool for this, but I think for this type of reservoir, we need more integration with seismic. We can, for example, use the pressure data to understand if one type of sand is in the same aquifer from another reservoir, and this can be very useful. But in my opinion, this approach needs more integration between seismic, petrophysics, geology, and we can use pressure to help us. And yes, that's it.
Okay, thank you, Bruno. And it looks like we don't have more questions, but I have one, and people in the chat can write the questions that if they had. While you answer my question, what kind of environmental factors make it difficult to interpret the raw pulse neutron data?
Yes, this is a good question. I think for example, when we have some problems with cement, cement can affect the results of the pulsed neutron. So we need to take care with this, and we need to apply these corrections in the raw data to have a better sigma curve, for example. And for example, there are some zones that we have many tubing or casing, very thicker tubing or casing, and it also can affect the pulsed neutron results. We need to apply some corrections for that. So that's why it is not good to use the raw data from pulsed neutron.
Okay, thank you, Bruno. And well, we don't have more questions. So I want to apologize with our audience for the bit transmission problems. I'm sorry. And so we will close this session, not before thanking our director Bruno for his wonderful presentation on petrophysics in mature fields in Brazil, and also our audience present. Do not forget to fill out the satisfaction survey that was passed through the YouTube chat. We look forward to joining you in future opportunities, Director Bruno. Thanks to all for attending. I hope all of you had a great day.
Thank you very much, Eric. Thank you very much for the audience. It was a pleasure to stay with you here today. See you soon.
Okay, thank you, Bruno.
Thank you. Ok, amigos.